Welcome to the Explainer. Ever wonder how a machine can learn to make decisions, kind of like we do, but with the cold, hard precision of math? Well, today, we're going to find out by building one of the most intuitive models in machine learning from the ground up.
You know, at its core, a decision tree is basically a game of 20 questions. Seriously, it starts with a big general question, and then each answer you give leads to another, more specific question until you've narrowed everything down to one single clear answer. It's this step-by-step logic that makes them so incredibly powerful.
Okay, so let's get familiar with the basic anatomy here. Every tree has three main parts. It all kicks off at the root node. That's where all our messy, unsorted data lives. From there, the tree branches out at these decision nodes, which are just the questions we ask to split the data up. And at the very end of those branches, you get the leaf nodes. Those are our final answers.
So here's our game plan for today. First, we're going to set up the problem. Then, we'll get into this idea of purity to figure out what a good decision even looks like. After that, we'll see how the tree picks the smartest questions to ask, watch it grow, and finally, learn how to trim it back to make it even better at predicting things.
Every journey in machine learning has to start with a question. So let's frame the puzzle that our decision tree is about to solve.
Okay, take a look at this. This is our data set. The mission, should we choose to accept it, is to predict whether we'll play tennis based on the outlook, temperature, and humidity. Right now, it just looks like a jumble of yes and no answers. But trust me, there are patterns hiding in there, and it's our decision tree's job to hunt them down.
So to find those hidden patterns, we need a really clear goal. For a decision tree, the whole point is to bring order to chaos, to take all this mixed up data and sort it into these perfectly clean, predictable buckets.
The key idea here is purity. Imagine you have a big jar of marbles with all different colors mixed together. That's impure. A pure group would be a jar with only blue marbles. Our tree's whole mission is to keep splitting the data until we end up with groups that are either all yes we play tennis or all no we don't, perfectly sorted.
So a group with an even 50-50 split of yes and no answers? That's what we call highly impure. It's totally unpredictable. On the flip side, a group that's all yes or all no, that has zero impurity. That's the jackpot. That's the state of perfect clarity our tree is aiming for.
But how do we actually put a number on all this messiness? Well, we have two main tools, Gini impurity and entropy. Now don't get bogged down by the formulas. Just think of them as impurity meters. They both do the same basic job. They give a score to a group of data. High score means it's a total mess, and a score of 0 means it's perfectly pure.
If we look at our starting data set, it's split perfectly down the middle, 4 yeses and 4 nos. This gives it a Gini score of 0.5, which is as impure as it can get for two classes. What that score is telling us is that if we just guessed the outcome, we'd be wrong half the time. Our job is to ask questions that drive that score down towards 0.
All right, now for the most important first step. How does the tree pick which question to ask first? Out of outlook, temperature, or humidity, which one is going to give us the most bang for our buck? We need a way to find the smartest question.
And this is where information gain comes in. It's just a way of measuring how much a single question helps us clean up the data. The tree basically runs a little experiment for each feature. It asks, if I split by outlook, how much purer will the new groups be? What if I split by temperature or humidity? The one that causes the biggest drop in impurity, the one that gives us the most information, wins.
And here's how the tree actually calculates that gain. It's a pretty simple 5-step process. First, it measures the impurity of the whole group before any splits. Then it just pretends to split the data by a feature, like outlook. It calculates the impurity for each of those new little groups, averages them out, and then just sees how much better it is than where it started. That difference, that's the information gain.
So when we run the numbers for the outlook feature, we get this nice high information gain score. The tree would then do the exact same math for temperature and humidity. Whichever feature gets the highest score, the one that gives the most clarity right off the bat, gets to be the first and most important question for our tree. It becomes the root node.
So now that we have our method for finding the best question, we can just let the tree grow. It'll just repeat this process over and over again, for every new branch until it has a clear path to every possible answer.
And there you have it, the final result. It started with outlook, and then at each new step, it just kept asking the smartest question for whatever little subgroup it was looking at. It keeps splitting the data until it gets to a clear yes or no. What we're left with is this perfect little flowchart of rules that it learned all by itself, straight from the data.
Now, you might be thinking that a tree that perfectly classifies every single data point it's ever seen is the best possible outcome. But here's the twist. In machine learning, being too perfect can actually be a huge problem. It's a classic issue called overfitting. So here's the deal. This algorithm, it's a perfectionist. It'll try so hard to get everything right that it starts making up rules for every little weird thing and outlier in the data it was trained on. It's kind of like a student who just memorizes the answers to the practice test instead of learning the actual concepts. Sure, they'll ace that one test, but they're going to bomb the final exam.
The solution to this is a technique called pruning. And yeah, you can think of it just like trimming a real tree. With pre-pruning, we set rules to stop the tree from getting too big and complex in the first place. With post-pruning, we let it grow totally wild, and then we come back and strategically snip off the branches that aren't really helping, leaving us with a much healthier, more robust tree.
So this really gets to the core trade-off with decision trees. Their absolute greatest strength is how simple they are. You can literally just follow the logic down the flowchart. But that exact same tendency to create super specific rules makes them really vulnerable to overfitting if we're not careful. Pruning is how we find that perfect balance between power and practicality.
And you know, this transparency isn't just a nice-to-have feature. It's absolutely critical in high-stakes fields like medicine. When a model tells a doctor a diagnosis, that doctor needs to know why. A decision tree can show its work, laying out the exact chain of logic it followed. It's not just a black box prediction. It's a reasoned argument.
So, to wrap the whole process up in a nutshell, a decision tree uses math to find the most insightful questions, asks them over and over again, and in the end transforms a messy spreadsheet into a clear, simple, and actionable flowchart of rules.
The real magic of a decision tree is its ability to make complicated things simple, turning confusing algorithms into transparent flowcharts. And that brings us to a final question for you to think about. What's a complex decision you face, either at work or just in life, that could be simplified by breaking it down into a series of simple, logical questions?